start with the first lecture this morning. Second talk of Jean-Benoît Bost about algébrisation technique in analytics, formal and diophantienne geometry. Okay, thank you for the introduction. So, yes, during the first lecture, we saw the proof of the following theorem. So we were considering some curve, some smooth projective curve. Embedded in the projective space, let's say over C. And you were given some germ of analytic surface embedded in Pn of C containing this curve. And we proved that when the normal bundle of C in V, so this is the line bundle on this curve, when this line bundle is ample, or equivalently if its degree is positive, then V, the surface V, is algebraic. In the sense that it's a risky closure, which is some reducible projective complex variety in Pn, has the same dimension as V itself, 2. Okay, so today I would like to make a series of comments concerning this theorem on its proof. So the key point of the theorem, of the proof, was to prove that the space of sections of analytic section of the line bundle O of D on this surface is finite dimensional, and actually we prove that it embeds in this space of what I did write gamma v hat OD, which was defined as the projective limit of the spaces of sections of OD on the successive infinitesimal neighborhoods of CI of C in V. So this is F infinitesimal neighborhood of C in V. So we proved that this is finite dimensional, and actually that the dimension of this space, hence of that space, is a big O of D squared. Okay, so today I would like to start with a series of comments on this. So the first comment is obvious, but of course, in this theorem, you may replace Pn by any quasi-projective complex variety. Still holds. With Pn replaced by any, let's say, quasi-projective complex variety. Let's say M. And of course, it's absolutely straightforward. If you have C in V, in M, you say, of course, M is in Pn, and the theorem inside the Pn gives you immediately a theorem inside M, of course. The Zariski closure of V in Pn is the same as in M. So this is obvious, but for applications, it's very important, of course, to observe this. And second comment is that actually analytic geometry play basically no role in this proof. And you have the straightforward extension of this theorem, of its proof, to the formal setting. Actually, to make this proof, to make this proof work, what do we need? We need to be able to consider basically the spaces. So the main ingredient is to have the successive CIs. So here, the CIs were projective curves, reduced, non-reduced, analytic compact spaces, but as you probably you certainly know that they are automatically algebraic, but you may copy this proof in a purely algebraic setting. So you may replace C by any field. The C, then you may take for C, let's say, a smooth, let's say, projective, let's say, geometrically irreducible curve over K. And then the CIs will be non-reduced curve. Such that the associated reduced curve, the underlying thing, is the same, always the same curve as the one we started with. And we need to know to have this, we had these short exact sequences short exact sequences of, let's say, current sheaves. And CI for every I. Okay, so we did use that. And from this data, you may define, let's say, some kind of Zariski closure of V. So it will be replaced by something. So maybe we can call this system V hat. And the Zariski closure of V hat will be the smallest closed so C is in Pn of k, Pn over k. So closed subscheme of P and k containing all the CIs in the scheme theoretic sense. So that is by definition, this is the sheaf of ideals of this Zariski closure is a subsheaf of O of Pn defined by functions that vanish on all the CIs, taking care of the multiplicities, on the non-reduced character of the CIs. Okay, so if you have such data, you can copy the proof in a purely algebraic setting. Faut utiliser ça? Yeah. C'est mal sinon? Oh. C'est très mal sinon? Très mal. Okay. So maybe I will not say too much about formal geometry, but if you are familiar with the very basic of formal geometry, you might check that zeta above correspond exactly to give V hat as a closed formal subscheme of the completion of Pn of k along C. This is a topologically ringed space. That is so its underlying space is the same underlying space as the one of the curve. And if you take U, some open subset in C, the sheaf of section of the structural sheaf of this formal scheme is defined as the projective limit of the O, or UI, where UI is the ith infinitesimal neighborhood of U in Pn. And of course, it is the same thing as a set. This is a set of section over U of O of Pn divided by E of C at the I plus 1. So, in formal geometry, we work with space that are ringed space, but these rings are equipped with a topology. And the topology here is a pro-discrete topology. So this is, let's say, a K-vector space equipped with a discrete topology. And here, the topology on the limit is the projective limit of this discrete topology. Okay, so this corresponds to the ad. So this was between brackets. This explains what is this formal completion. And this, the condition above means exactly that V hat is formally smooth of dimension 2. Okay, so the point is that, well, I don't want to take too much time discussing the basics of formal geometry. In a sense, it's extremely boring. But formalism is exactly devised to, let's say, to mimic analytic geometry, but in such a way that if you take, for instance, if you are in the situation of the proof of these theorems, there's purely algebraic data that constitute the bones of the proof corresponds exactly to this notion that corresponds to, okay, intuitively to the analytic notion in a situation where you are in a much more algebraic setting. Okay. Okay. So this second comment. A third comment I would like to make is that the theorem, or its formal counterpart, well, the proof is very robust and very simple, and it extends to much more general situations. So you have some, let's say, higher dimensional generalizations. But for instance, V, so you may replace C by projective by M, let's say, projective subvariety of Pn. on V by some V germs. Containing M. Okay, to make the proof work, you need some amount of, let's say, smoothness, of regularity to have the analog of the above exact sequences. So, for instance, you may ask V to be smooth. So it's, well, subvariety is not clear what it means, but V smooth manifold. And for instance, you may ask M to be a divisor in V which is smooth, or you may also work with higher codimensional M in V. So you may ask M to be, let's say, locally complete intersection LCI in V. So here you have some smoothness assumption of this kind. And of course, the most important condition is some kind of positivity condition on the normal bundle that will allows you to bound the dimension of the space of section of OD. So you need some positivity assumption. On the normal bundle on V of M in V. So you see, under these conditions, with Fm is LCI, you have some well-defined normal vector bundle. So, for instance, if this vector bundle is ample, the same theorem holds, but ampleness is a quite, well, the proof will work with much weaker condition than ampleness. You may ask ampleness on some, let's say, generic curve in a family of curves that really moves in M. Let's say. Let's say a family of curves that moves, that covers M. This will replace this positive degree assumption, and all this implies but for us it will not be important, but you have to know that it exists in this setting. And the last point I would like to make concerns the analogy between this algébrisation theorem and Chow's theorem. So, I want to say. say, comparison. Okay, so recall, you have seen this in Carlos' lectures last week, that if you are given M, a compact, let's say, connected, C analytic manifold, of dimension D, and if you are given L, a C analytic line bundle on M, then you may prove that the space of global sections of L of its power on M are finite dimensional, and that their dimension grows like D at the power, no, let's say, of dimensions little n. The dimension of the section of L times D goes like the nth power of D. So this statement is formally analogous to the one. Okay, here, actually, we did use it for O of D, but it is true for the power of any L. And of course, 2 is a dimension of the space we are interested in. And here, we can prove the same kind of upper bound. You see this, I suppose, Carlo explained you this old argument that occurs in Siegel's proof, or that actually, I suppose, is due more or less appears already in Serres, in work in Cartan's seminar, and actually that kind of argument, as far as I know, goes back to Poincaré. And from this, you may deduce basically some version of Chau's theorem by the same kind of argument. If you have if you assume that M is embedded, say, analytically in the complex projective space, you may consider the Zariski closure of M in the projective space. Of course, it contains M. And you may prove by the same argument that the dimension of the Zariski closure of M is its dimension n. So, of course, yeah, as it contains M, it's very easy to see that it is at least n. So the key point is upper bound. The fact that this Zariski closure has dimension at most n, and the proof goes by the same kind of argument. You may embed the space of section of O of D on this Zariski closure by restriction. Any such section, algebraic section, define an analytic section of O of D over M. And this map is injective by the very definition of the Zariski closure. If you have a section there that vanishes on M, it vanishes on its Zariski closure, so it did already vanish. And you get, in this way, that the dimension of this space this big O of D at the end. But here again, by the theory of the Hilbert polynomial, this grows at least as fast as the dimension of at D at the power of the dimension of the Zariski closure. So from this, you get the fact that the dimension of the Zariski closure is at most n. Okay. So I would like to, at this point, I would like to give to you some exercises to elaborate on this argument. So, okay, the point is that this argument doesn't really prove this. This argument proves less. It proves that, in a sense, M is a component, analytic component of this or something like that. So, to complete the proof of Chiao's theorem, so the proof of this, so complete the proof of C by combining so what we have proved, so the equality, so star, this equality, and also some, maybe you will need some basic facts about the regular points. Of, let's say, complex algebraic varieties. So if you have given a complex, let's say an irreducible complex algebraic variety, you have to know that regular points form an open dense, an open Zariski dense subset of it. And the following topological facts that are not completely obvious. So let I state as stop. The following thing. So let X be quasi-projective reduced scheme okay, it may look pedantic to say quasi-projective scheme, quasi-projective reduced scheme. It's a quasi-projective variety in the sense of Serre. But the word varieties has so many different meanings in the literature that it's better to avoid it in general. So that's what I mean. Okay, so you know that you have then you have the Zariski topology and the analytic topology on the set of complex points of X. So basically, the Zariski topology is the Zariski topology, and the analytic topology is the topology induced by any embedding in Pn of C given by the quasi-projective structure. It doesn't depend on the choice of the embedding. So you will need the following two facts. If U is some open dense subscheme of X, then the set of complex points U of C it's clearly open, more or less by definition of the analytic topology, but the point is that it is dense in X of C equipped with the analytic topology. And the second fact you will need is that if X is connected, so it means that it is connected in the Zariski topology, or connected as a scheme, it's the same thing. Then X of C is connected in the analytic topology. I do not claim that this assertion top is trivial. Indeed, it is not. But I claim that if you admit this and you come back, that basically using it, you can complete the proof of Chow's theorem. Okay. And the second exercise around Chow's theorem is the following one. Here, we base the proof of Chow's theorem on this very general statement concerning any line bundle on any compact connected analytic manifold. But actually, in the proof, we work with a much more special compact connected manifold, namely a compact connected manifold that is embedded in the projective space. And we need this only for O of 1. And I claim that in this case, it's very elementary, complex and geometry and topology gives you an argument. So I will sketch an argument, and the exercise is to make the argument rigorous, right? Okay. So compact, complex, let's say, connected analytic submanifold. So prove this estimate for O of 1. So prove directly. As follows. Okay, so the following argument, actually, it's an argument that appears in Poincaré. Maybe it's not that well known, but Poincaré is well known for many things. And in algebraic geometry, it is known for some very important theorem about abelian varieties, Poincaré reducibility theorem. So this theorem appears in a very interesting paper in ACTA, which is called something like Sur les variétés abéliennes. And as far as I understand, Mittag, Lefschetz asked Poincaré to write some kind of review article on abelian varieties, and Poincaré, okay, proved a lot of very interesting things. I suppose it's related to the fact that Riemann had announced a lot of deep results concerning theta functions. Basically, I suppose Riemann announced in some lectures that any rational function on an abelian variety was a quotient of theta functions. And as far as I understand, it was more or less proved by Weierstrass in his lectures in Berlin. But of course, neither Riemann nor Weierstrass published proofs, and it was in the decades after the Franco-Prussian War. It was apparently at some point it was a very a tricky point of competition between the French school and the German school. On Poincaré and Picard did write an article on this question, or at least a compte-rendu note. And at some point, I suppose Mittag-Leffler wanted to take advantage of the situation to get some interesting paper from Poincaré. So in this article, actually, in a sense, Poincaré gives a proof of Chau's theorem. Well, he is interested basically essentially only in abelian varieties. So at some point, you work with, let's say, complex analytic abelian varieties defined by the quotient of CG, by some lattice associated with some Riemann matrix, blah, blah, blah. And you produce theta functions, and it's not too difficult to prove that there are enough theta functions to embed analytically the complex abelian variety in the projective space, and you want to know that it is an algebraic variety. So you want to prove Chau's theorem for abelian varieties. Of course, you can prove that by giving some precise analysis of the algebraic relations between theta functions. But Poincaré gives an argument that is quite general indeed, on which, as far as I understand, basically proves Chau's theorem. But of course, this argument is maybe not completely rigorous, and it's not that easy to elucidate. And of course, in this paper, Chau doesn't quote Poincaré. And if you look at the analysis of Chau's theorem in mass reviews, it was written by Henri Cartan, that says, of course, it proves something that it's expected for a long time, but it doesn't quote Poincaré either. So here is Poincaré's argument.
You mean growth of most as the end?
Oh, sorry. Thank you. So you prove something that is indeed quite related to what was proved in the analytic proof à la Siegel. Ah d'accord. C'est pas clair. D'accord. So you choose a point O in M, and you want to prove that for C large enough, C positive integer large enough, the map let's send a section here to a jet of order CD. So, okay. So, how do I write this? So I-O is the idle sheaf of O. When you have a global section, you can you may look at it. You may look at its Taylor expansion at the point O and M, and you may look at the coefficients of the Taylor expansion of degree smaller than CD. Okay. So of course, it is something finite dimensional, and it's very easy to see that the dimension of this is big O of D at the M. And the point is that this map is injective. So it means that if you have a section that vanishes with a large multiplicity of the order of D at a point O, it has to vanish. If you prove this, you are done. Because on this, of course, if M is one-dimensional, it's basically clear. We see, but which is the degree of O of 1 on the analytic curve M. Okay, that's a very definition of the degree. And on a compact Riemann surface, a line bundle of negative degree has no global sections. You don't know to know anything about algébrisation to prove that. Okay, and you may reduce to the one-dimensional case by considering intersection of M with linear subspace that contains O that are general enough. By restricting to M inter V, where V linear subspace of Pn containing O transverse to M of codimension the dimension of M minus 1. So using techniques that are completely standard today, a little bit of transversality using Sartre theorem, it's very easy to see that you have, let's say, an open subset in the Grassmannian of such spaces that satisfy non-empty this transversality condition. When V varies in an open subset, this is a family of curves of fixed genus. So you have this kind of vanishing argument in all the fibers, and if it vanishes in all the curve sections, it vanishes everywhere. So using this, by this, you can very easily make the Poincaré's argument correct and give a very simple proof of Chau's theorem. Okay? Okay, so this was supposed to be the content of my first lecture. And now today, I wanted to give some, to go one step further in the algébrisation theorems. So you see, in these theorems, we didn't use any kind of cohomology, at least explicitly. We did some count of dimension count, and it was enough to prove algébrisation theorems. Now I would like to, in the next lecture, in my today's lectures. My aim is to explain the content of SGA2 that is devoted to some version of Lefschetz theorems obtained by using algébrisation techniques in formal geometry. So the point is that SGA2, among the SGAs, maybe it's not the most popular, and a good reason for this is that, I suppose, it has not been rewritten. The available version is exactly the original version of the seminars. SG1 has been rewritten a lot. The present version is on many other ones. So when you read it, it's maybe not that easy because okay, it's the first very bright, but it's in any case the first version. So I would like to explain the content of SGA2 that has to do with algébrisation of vector bundles, of sections of vector bundles. And I suppose it's important to have some general idea of the history of the subject. The second lecture was. Okay, so it's called cohomologie locale des faisceaux cohérents et théorèmes de Lefschetz locaux et globaux. So the point is that there is a lot of local algebra in SGA2 that makes maybe the very geometric ideas that lies behind the theorems not that easy to grasp at first sight. And but of course that in the long run have been quite important because there are many applications of SGA2 now to local algebra, to the kind of deep local algebra you need to do in arithmetics when you are interested in formal spaces of deformation of representations of profinite groups that play an important role in, for instance, White's type proof. So, but for this reason, it's very important today. But now I would like to focus on the very geometric ideas. And I will use also some kind of complex analytic variant of the theorems. So it's called Lefschetz theorems. So I would like to start by some kind of historical discussion. And so, it's like in the guide vert, un peu d'histoire. So, the Lefschetz theorems alluded to in the title of SGA2 are theorems of this kind. Let's say in the most, I suppose Carlo also discussed some of them last week. You start from, let's say, some projective, smooth projective variety, so analytic or algebraic, it is the same. Now we know how to prove Chau's theorem, let's say of some dimension n. It's connected. When you consider some hyperplane section, y, that we will assume to be smooth, say for simplicity. On the Lefschetz theorems, so that goes back to the book of Lefschetz in 1924, which is called L'analyse situs et la géométrie algébrique. Analysis situs is an old terminology for algebraic topology. gives some, well, explains how the topology or invariant of algebraic topology of X and Y are related. And maybe the strongest version of Lefschetz theorems is to say that, well, it's not stated like this in Lefschetz, but basically all the ideas are there, that the relative homotopy group of X, Y vanish for K at most n minus 1. And the very point is that here, in the complex topology, you may obtain X topologically from Y by adding cells of dimension n or higher than n. Nx maybe obtain topologically from Y by gluing, adding cells of real dimension at least n. Sorry?
The smoothness of Y.
No. Wow. For this simplest statement, I prefer not. This is true. Well, we will see statement by purely algebraic means where it can be, the smoothness is not important. But for the purely algebraic, purely topological settings, I suppose also here it's not important, but it's not that easy. So I did write, well, a difficulty in this theorem is to remember the statement because you have assertions that depend on the dimension. So that's something you can recall, you can remember. Easy, and you can think of the, let's say, one-dimensional case to recall if it is n or n minus 1. And concretely, for instance, it implies that the map, for instance, HK is an ISO and is injective for K equals n minus 1. No, it's onto. And in cohomology, you have analogous statement, but you have to hetchan X and Y, and you have replaced to onto by injective. Okay, but you have this version or that one is stronger because, for instance, you have the same kind of argument for homotopy group. So it's a very, very strong statement. For instance, once you have chosen a base point. Well, actually, in a sense, the terminology Lefschetz theorem is not very fair, especially if you consider the versions proved in SGA2. Because that kind of statement was discussed already in an incredibly beautiful paper of Castelnuovo and Enriquez about 20 years before. So let me explain. And actually, well, of course, generally speaking, mathematical terminology is not very fair. But in this case, it's somewhat shocking. So it's in the Annals of the École Normale in 1906. 23. So the point of Castelnuovo and Henriquez is, well, they explain in the introduction the following things. Okay, initially one did study curves, and then we went to the study of surfaces, and surfaces are much more interesting, but much more complicated than curves. And now we want to look at, let's say, three-dimensional algebraic varieties, and you can expect things like fundamental group or homology, first homology groups, and or differential forms, one forms, to be still more complicated than for surfaces. But no, it's not more complicated because you have these Lefschetz theorems. So they prove that, okay, if dimension of x is plus 3, then with the same notation as before, the restriction map from one form on x to one form on y is an iso. So they prove that kind of invariants that were attached to x and y by Italian geometers, so by Max Noether. Max Noether was the first to observe or to prove that the dimension of the space is a birational invariant. So it proves that these invariants are unchanged when you go to hyperplane sections, and also for, let's say, for homology groups. And related to that, they prove a lot of very interesting things. For instance, they prove that the dimension, something that goes from what's proved in the two-dimensional case, that the dimension of H1 is twice the dimension of omega 1. Come from Hodge theory, but it was only proved by for surfaces by Picard and maybe Henriquez. It was definitely not trivial. So it's also in. So, oh, sorry. And they also prove in this paper, for instance, using this, that any abelian variety is a Picard variety of some abelian surface, of some surface. Because you start from a large dimensional abelian variety, and you take successive hyperplane sections, and the abelian variety will be the Picard variety of this section. Well, Betti numbers. Betti numbers are the same. The proof is, it's of course, they say that the Betti numbers are the same, but it's clear from the proof that responds to that the canonical map is an isomorphism. And actually, in the paper, they quote Picard, and actually Picard did prove, and it appears in his book with in Picard Simard. So, for instance, you can find in volume 1, page 86, the fact that, okay, maybe for dimension 2, or Picard's argument seems to work in higher dimension 2, that H1 of the hyperplane section okay, here I give you the page because personally I have not been unable to figure whether it's possible to give a rigorous meaning to Picard's reasoning to prove that. It's very. Sorry? Or pi 1 of y. He has a way to explain, okay, you take a surface, okay, an hyperplane section, and you have there is some reason why any loop in the surface may be deformed to the hyperplane section. But it's quite short, and I am, okay. So maybe you can have a try to prove that, okay, it was already in Picard. Okay.
The second author is Picard, then?
So,
You wrote Picard?
on Simard. So there's this book by Picard Simard on the algebra. It's Picard, I suppose Simard was working also as a teaching also at the École Polytechnique or something like that, and did write the lessons. Okay. Okay, so this is one. This Lefschetz type theorem are one part of the origins of the results in AGA2. There is another line, another circle of results leading to AGA2 that are precisely the algébrisation results in analytic geometry. So this is one. On the second origin of AGA2 are algebrizations of analytic objects. Well, maybe when I arrive, I can make some comments. It's very interesting to observe that Lefschetz doesn't quote the paper by Castelnuovo and Enriquez, and I suppose the reason for this is that it's that easy to make the arguments rigorous, and in a sense, these arguments are very modern. They really use some arguments using some kind of rigidity for families of Hodge structure. It's very interesting to, okay, if I have time, I can try to sketch the arguments. And I suppose the very lack of foundations for that type of argument, I suppose largely explains why they have not been really developed or recovered or used in some other setting for a very long time.
Or is Lefschetz's original argument correct by rigorous by modern standard?
I would say, well, yes, more or less, yes. The point is that there is also this hard Lefschetz that is not correct or very difficult. At least it's very difficult to give it a precise meaning. But I suppose this part is more or less correct. The point is that, in a sense, he gives some arguments to prove what can be proved by a Morse theory, these assertions of the topology of X from the one of Y obtained by adding cells. And it's okay. So in the genealogy of AGA2, you have another part, which is the algébrisation of analytic objects. So of course, we have already discussed this when we discussed Chaux's theorem. But as far as I know, from let's say modern, of course, it's a very old thing in Newton. So you have things, functions, algebraic functions, and transcendental functions, and so on. But from a modern, I suppose, from a modern approach, the first important contribution is the one by Puiseux. It's a very interesting paper. So it's before Riemann. And one of the things he proved in his paper is that, okay, you take a polynomial, it's a non-constant polynomial, in two complex variables, and the fact that Puiseux proved one of the part of the assertions stops in the exercise 1, Puiseux proves that if P is irreducible, then the plane curve C, defined by the vanishing of P, you are also allowed to delete a finite number of points, singular points, for instance. So this is always connected. Okay, this paper is not too well known today, but I suppose it plays a very important role in the history of mathematics. It's basically one of the first papers when there is a relation between, let's say, monodromy in the topological sense, because you understand the algebraic curves you look at this set as a set of points in C2 and use the topology on C2 and blah, 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 and continuation. So monodromy on purely algebraic phenomena. And actually, when Hermite read Puez's paper, he wrote a very short and very interesting compte-rendu note where he explains the relation between Gauss theory and the theory of the fundamental group for Riemann surfaces in modern terms. And before Puez, it was not known. And of course, Riemann in his famous paper on Riemann surfaces, was dealing with Riemann surfaces. So for Riemann, a Riemann surface is not a Riemann surface as defined today. It's a Riemann surface plus a morphism to P1. So Klein is very proud to have invented the modern definition where you don't give the morphism to P1. As far as I know, Klein was the first mathematician who had the bright idea to edit his own complete works, because in this way you can prepare your own comments on your work, so it's safer. It's one of the things he really insist on. That Riemann, okay, he was very bright, but okay, Riemann surfaces should be Klein surfaces, well, it's implicit, Klein surfaces. So he worked with a Riemann surface, compact connected Riemann surface plus a morphism, finite morphism. Well, today we say finite morphism. Of course, in old literature, it's a ramified covering. So he proves that any Riemann surface in this sense is algebraic. So it corresponds to, let's say, some plane curve. Well, up to some finite point. You have to normalize some finite sets. Where P is as before, okay? And of course, in this thing, the coordinate x corresponds to nu. And the point is that you have to find some meromorphic function on C that will play the role of y. And the point is, y is a meromorphic functions on x generically injective on the fibers of nu. And the point is that the existence of this additional meromorphic function is obtained by some kind of elliptic analysis. You use the Dirichlet principle that at this time was not well justified to solve, let's say, the Cauchy-Riemann equation, well, the Laplace equation, and then the Cauchy-Riemann equation on the surface. So it corresponds. Use elliptic analysis. Dirichlet problem. Okay? So, in this story, of course, a related one of the next step, logically the next step, is the theorem of Chow. So, Chow's theorem was published in 1949. But actually, chronologically, some much earlier, very important algébrisation theorems was proved by, let's say, Poincaré, Lefschetz, Hodge. So it's in 1941. On Grothendieck and Spencer. In 1953, that, okay, you take X, let's say, a smooth projective, so algebraic by Chow's theorem, and the theorem of these people assert that any analytic line bundle over X is algebraic. So, of course, it's basically the content of the theorem of Lefschetz on 1-1 classes. So recall, you take alpha, a class in H2. To say that alpha is algebraic, is to say that alpha is a C1 in modern terms of some L, while S is some algebraic line bundle on X. So if you have an algebraic line bundle, it's given by, okay, you cover X by the risky open subset, and you have a cocycle given by some regular functions by units on the intersections of the set of this cover. And you want to prove on analytic is the same thing as analytic thing. So it's the same thing as that. And this is equivalent to say that alpha is Poincaré dual to the class of some divisor, algebraic. Divisor on X. Of course, if you know Chow's theorem, an algebraic divisor and an analytic divisor are the same thing. And to say that alpha is let's say, you could say that alpha is analytic. It's not a standard notation. By saying that alpha may be written as C1 of L, while S is an analytic line bundle on X. And the point of Grothendieck and Spencer is to use, okay, basic shift theory, okay, to give a meaning, of course, to an analytic line bundle, and to say that this is equivalent to the fact that alpha, since the complex number is in H1. This, okay, you look at the point of Grothendieck and Spencer. One of the point of Grothendieck and Spencer is this. And you have the exponential map. So you see that a class here, well, you look at, you have the map from H1, the analytic picker group goes by C1 to H2 and goes by this map to H2XOX. And the fact that some class alpha here goes to 0 is exactly this property. Okay? So basically, to know that any one class is a class of a divisor, so to prove Hodge conjecture in dimension 1, you need to prove basically that an analytic line bundle is an algebraic line bundle. And that indeed what Grothendieck and Spencer did in their paper by a completely new argument compared to the old arguments of Poincaré and Lefschetz. The argument of Poincaré of Lefschetz was an argument using normal functions, so Lefschetz, Spencer's, on sections of the relative Jacobians and so on. Okay? So to prove this, Grothendieck and Spencer use some new techniques involving cohomology groups, and this new techniques is a key point in the proof of Gaga by Serre on HGA2, and actually the same argument plays a key role in the solution by Grauert of the Levy problem and so on. And okay, so that's what I wanted to explain today, but I suppose I should stop here for today, and I will explain this tomorrow.